In part 1 of this video, we created two sets of normally distributed random variables called A and B. Each set had almost 1,000 numbers in it. Then we created a data set from the sums of A and B by adding each pair of numbers in each row, and we created another data set from the differences between A and B by subtracting B from A in each pair. After we created this table, we plotted all four databases on a line chart. On the x-axis, we had numbers from 1 to 990 something that showed what row A and B came from in the table. And on the y-axis, we plotted the values for A and B, which hovered around 100, but thinned out to about 70 at the lowest extreme and to about 130 at the highest extreme. And we decided that this is what we should have expected because we made the table using a formula for A and B that set the average to 100 and the standard deviation to 10. And we know from our statistics classes and from any textbook or from Wikipedia or online that in a normal distribution, almost all the numbers will fall in a range between 3 standard deviations below the mean to 3 standard deviations above the mean, which means the values fall within a total range of 6 standard deviations. So you could say that we tested the idea that if you had 1,000 numbers, you could just look at the numbers that are the farthest from the mean, above and below, and use the range between them as a method to estimate standard deviation. And you might say we validated this method by first applying it to the variables A and B themselves. The total range between the most extreme values was about 60, and if that is 6 standard deviations, then 1 standard deviation must be 10. Voila, it works. We expected it to be 10 because we made it 10 in our formula. So then we used that method to estimate the standard deviations for the sum and the difference data sets. And we found them both to be about 14, maybe something close to 14.15 as an average. I'm trying to make this picture clear because the idea that 6 standard deviations can be used to basically define what is normal is one of the major foundations of quality control. And I want it to become automatic in your minds that if you have a normal distribution, you can relate the range of measurement values to a span of 6 standard deviations. But at the same time, I want you to get a picture of how we need to deal with numbers for things like measurements that are somewhat uncertain, so we call them variables. And now that we have this picture in our minds, I want us to move on in part 2 to the spreadsheet and see if we can learn something about why the variation for the sum or the difference of our two variables A and B seems to be about 1.4 times the variation of the variables themselves. This was originally one video that I chopped in half, so hang on while we go through this transition. I want to wrap this video up in about 5 more minutes.
No way.
So hang in there, and I'm going to speed
this next section up for you a little bit.
Oh, that's all right. Actually, I'm speeding up the video and keeping my speech normal. You may have noticed that every time I enter something, all the random numbers refresh with new random numbers, and all the calculations have to be recalculated, and the charts change. And with 2,000 random number formulas and a couple of calculations based on them, this slows the computer down. But it also turns random number experiments into living examples of variation over time. So each time the screen refreshes, you get a new sample of random numbers, and you see how estimates vary in each case. And this is like the real world. Sometimes things come close to expectations, and sometimes you're disappointed. So what you see me doing here is entering formulas for the average, the standard deviation, and the variance of the numbers in each column. I don't often use the formula for variance, so as you may have noticed, I typed it wrong. It should just be the abbreviation VAR and the parentheses and not the full word. Some of you may know that variance is the square of the standard deviation, which is equivalent to saying that the standard deviation is really the square root of the variance. I'm hoping that you're all comfortable with square roots. So I've written formulas for the average, the standard deviation, and the variance, and now I've copied and pasted them across the top 3 rows of the spreadsheet. And let's look at these numbers. The averages are on top, and you can see that for variable A and variable B, the average comes close to the expected value of 100. We expected that because way back in the beginning, in the random number formula, I chose a value of 100 for the mean. Now notice that the average for the sum of variable A plus variable B comes close to 200. Does that make sense? Well, it should, because adding two numbers that are close to 100 should get us a result that's close to 200, especially when you take the average of doing this 1,000 times. Similarly, for the difference between variable A and variable B, subtracting the number that is close to 100 from another number that is close to 100 should give a result close to 0, especially if you do it 1,000 times. So there are really no surprises in the averages. Now let's look at the results for standard deviation. Just like for the mean of 100, we chose 10 for the standard deviation of our random numbers way back when we wrote the formula for variables A and B. But now look at the standard deviation for the sum and the difference of these pairs of variables. What do you see? Yep, something very close to 14. Sometimes even close to 14.1 or 14.2, like we estimated from the line graph earlier in our experiment. So what's going on? What's the mathematical root by which adding or subtracting two variables, each of which has a variability that can be expressed as a standard deviation of 10, how does that yield a sum or a difference that has a variability that can be expressed as a standard deviation of 14, more or less? So let's look at variance. For the variables A and B, the variance comes close to 100, which is what we would get if we calculate the square of the standard deviation, which is 10. 10 squared is 100, so that makes sense. But for the sum and for the difference, look at that. It seems like in both cases the variance is awfully close to 200. Is that just a coincidence? Or might we take an inductive leap with our minds and guess that the variance of the sum, or the difference of two variables, is equal to the sum of the variances of the variables themselves? Or we could go to Wikipedia and go down the page a ways, and beneath all these fancy formulas, in a section on properties of variance, is the statement here. One reason for the use of the variance in preference to other measures of dispersion is that the variance of the sum, or the difference, of uncorrelated random variables is the sum of their variances. And then this equation says the same thing. The variance of the sum of a bunch of variables, x sub i's, is equal to the sum of the variances of all of those x sub i's. And this statement is called the Bienaymé formula. It was discovered in 1853, and that was over 50 years after Carl Friedrich Gauss is thought to have first discovered what he called the normal distribution of errors. Maybe if Mr. Bienaymé had had access to computers and Google Sheets or Excel, he could have discovered his formula in less than 50 minutes, like we just did. What I want you guys to appreciate here is that with some basic skills, a lot of copy and paste, you can gain valuable insight into statistics and the concepts that quality control is built upon. Now, I've taken a little over 5 minutes from when I promised to wrap this up. Can you give me just 2 more minutes? We got to go back and look at 2 more things. First, we got to explain why the standard deviation of the sum, or the difference, is roughly 14. Actually, that's easy. Remember that we said the standard deviation is the square root of the variance. Well, that's the square root of 200. In a spreadsheet, you can write a formula for square root as the number to the power of 0.5, or 1/2. So poof, the square root of 200 is 14.14, and that explains the standard deviation of the sum or the difference. Some of you might also understand that the square root of 200 can be thought of as the square root of 2 times 100, which can be broken down into the square root of 2, which is 1.414, times the square root of 100, which is 10. If you understand this, you've come further than any student in any of my classes so far. But I honestly think that if you can put together the pictures I've presented to you in the line graphs, with the formulas that I entered into the top 3 rows of the spreadsheet, and follow the logic I've laid out during the past 5.5 minutes, every one of you could understand this. That may be wishful thinking. If you don't understand, don't feel too bad, because it took me practically half my life to get this. And the light bulb finally came on when I read the sentence that I read to you from Wikipedia. Alright, go ahead and take a nap if you want, while I clear up one final thing, and that is to show you that the value of 100 that we got for the variance of each of the 2 variables, and the value of 200 that we got for the variance of the sum of the 2 variables had nothing to do with the similar numbers we got for the averages of those same numbers. For one thing, say for example the value of 100 for the average was in feet. Then the value of 100 for the variance would be in square feet. 10 feet times 10 feet. The standard deviation squared. Because variance is in terms of squared deviations. And notice that standard deviation of variable A or B about the mean is the 10-foot length of any side of the square, which is the variance, which is 100 square feet total. So once again, the fact that the mean is 100 has nothing to do with the variance being 100. Similarly, the value of 200 for the sum of the 2 variances is really 200 square units, which gives a square root of roughly 14 linear units. And that's very different from 200 units in the average for the sum. I can illustrate what I've been telling you by changing my random number formula to have a standard deviation of, say, 5 instead of 10. Now watch the standard deviations and the variances in the formulas maintain the same relationship that was discovered by a friend, Mr. Bienaymé, in 1853. Let me go through that a little more carefully. We haven't changed the mean, which we're leaving at 100, but we changed the standard deviation to 5 in the formula for the first number in the variable A list. Then we copied that new version of the random number formula to all the cells in the full lists for both variables A and B. Now, when we look at the numbers in the top three rows that compute the actual mean, standard deviation, and variance for the data sets below, we see that the mean is still close to 100 for variables A and B, and 200 for the sum, and 0 for the difference. But the standard deviation is now close to 5 for the variables themselves, and about 7 point something for the sum and for the difference. And 5 is the square root for a variance of 25, whereas 7 point something is the square root for a variance of 50. And once again, Bienaymé's formula would have told us, or tells us, to expect a variance of 50 if we add or subtract two numbers that each have a variance of 25. So to summarize for both cases, when the standard deviation of A and B was 10, the variance for both was 10 squared or 100. And Bienaymé tells us that the variance of the sum or the difference will be the sum of the variances, which are both 100, so that's 2 times 100. And we can get back to standard deviation for the sum by taking the square root of 2 times the square root of 100, which is the square root of 2 times 10, which is 14.14. Similarly, when the standard deviation of A and B was 5, the variances were both 25, so in this case, Bienaymé tells us that the variance of the sum or the difference will be 50, or 2 times 25. So the standard deviation of the sum or the difference is the square root of 2 times the square root of 25, or the square root of 2 times 5, which is 7.07. Notice that in both cases we could generalize that when the standard deviation of two variables is the same, the standard deviation of the sum or the difference will be increased by about 1.4 times. I don't know about you, but this kind of experiment helps establish the neurological connections that tell me that Bienaymé was right. It helps me remember what he was right about, and also helps me think how I might be able to work with this idea in practice when I need to. So voila, and merci, Monsieur Bienaymé. Pardon my French. Okay, you ready for the quiz? Get set, go.